Have you ever wanted your personal AI assistant to self-evolve and adapt to your preferences simply by you using it without any explicit training? This week's trending AI research, OpenClaw RL from Princeton, demonstrates exactly that. Imagine a scenario where a student uses OpenClaw to help with homework but doesn't want the answers to sound AI. And on the other side, the teacher uses OpenClaw to grade those assignments and wants the feedback to sound natural and friendly. In short, both personas want their AIs to be personalized. In the paper's experiment, the authors simulated the two personas interacting with their respective AIs through the task of simply doing homeworks and grading them. And over time, using the paper's proposed algorithms, both OpenClaws self-evolved to become much more personalized to their users' preferences, validated by the much improved personalization score before and after the experiment. This improvement doesn't come from prompting. The changes are reflected in the model's weights and persistent going forward. So how does it work? The author starts the paper with a simple but keen observation that motivates the work, which is that every time we interact with an AI agent, we're already generating useful training data. But instead of using them, they're simply discarded. The authors call the data next stage signals. A next stage signal is anything that happens after the agent takes an action. It could be a user reply, a tool execution result, an error message, or even a GUI state change. For example, if the user re-asks the same question, that likely means the previous answer wasn't good. So OpenClaw RL proposes turning these next stage signal into a continuous reinforcement learning signal so the agent can improve directly from real interactions with the users. The framework extracts two types of information from these signals. The first type is evaluative signals. These signals simply indicate whether the agent's previous action was a success or not. A process reward model examines the agent's response together with the signal and assigns a reward such as a +1 for good or -1 for bad. The signal allows the system to perform reinforcement learning. The second type is called directive signals. These signals are even more powerful as it allows the model to know how a new response should be different. For example, a user might say, "You should have done this and that." To capture this richer signal, the paper introduces a method called hindsight-guided on-policy distillation, or OPD, which in short turns these user feedback into token-level learning signal, so the model learns how it should have answered differently. Both evaluative and directive signals are then combined during training via PPO-style reinforcement learning objective as the user interacts with the agent. The research conducted several experiments that showed that this approach can quickly personalize agents. In the simulated student scenario that we talked about, after only a few dozen interactions, the assistant learned to avoid overly structured AI-like responses and produced much more natural solutions. The authors also tested the approach across terminal agents, GUI agents, software engineering agents, and tool calling agents, etc., and saw similar improved performance.